anode to the cathode. The anode is negatively charged, the cathode is positively charged.
Okay, very simple. So again, with our device, okay, you have anode oxidation, cathode reduction, electrons from the anode to the cathode. So we separate them so we can harness that electricity going through. And then at the anode, because that strip of zinc or whatever metal you have is dissolving as it becomes ions, this will disappear. And then on the other side, the cathode side, the ions in solution actually become pure element. So they plate onto there. And actually, if you have old, if they say something is like silver plated or gold plated or whatever, they can take that piece of jewelry and stick it in there, and as long as there's silver ions, the silver ions will become pure silver and stick all around it, and then you plated it with silver. Or if you've got old silver spoons and knives and stuff from like ancient grandmother or something, they can stick them in silver nitrate solutions like that and plate the silver onto those spoons. Yes?
Is the anode reducing or oxidizing?
Anode is oxidizing. And I have that on the next page. These are kind of the different parts to your cell. And then in blue at the bottom, I have electrons flow from the anode, which is oxidized, to the cathode. So here's kind of the I don't want to say the tricky part, but we're talking about getting voltage and the electron going through the wire. Why does the electrons go through the wire? And that's because of the difference in potential. So we call like electromotive force. The cell potential is the electromotive force that like draws the electrons through the wire, that difference in potential. And the unit of that is the volt. So you buy like a 9-volt battery, or your little AA batteries are like 1.2 volts each or something like that. And I realized last period I spelled coulomb wrong.
You blew it.
I know.
Mistake.
C-O-U-L-O-M-B, coulomb. Coulomb's a unit of charge.
Who realized that?
I did. Like I was looking at it and knew it didn't look right. And the back of the sheet I gave you has the list of standard reduction potentials from your book. So again, you don't have to flip back and forth during your homework. There's also a list on the packet you get for your tests, but the list in the book is more inclusive, and you're going to need that for some of the homework problems because they use that list.
Go. Do it.
All right, so the zero voltage is the standard hydrogen electrode, and basically they made cells, I don't know who they are, but cells were made with hydrogen and all these other things, and then the potential was measured, and we get all these values here. So if you look up on that initial cell and you find the copper 2 plus becoming pure copper, there's your reduction of copper right here with 0.34 volts. But the zinc one is actually down here, and that was negative 0.76, but it was flipped over, reversed to make it oxidation, and becomes positive 0.76.
Raise your hydrogen peroxide.
I don't know if that's any good. I'm not into. Oh yeah. For what?
So I guess we'll add this hydrogen.
Oh yeah. Yes. That's what. Got it.
That's
It was in the box?
up there? No, it wasn't.
Oh no, I need that for demos today. Let me buy new
This one
stuff.
wasn't the last one.
Let me buy new stuff. Okay. Anyway. So what you guys are going to find is you're going to have to construct your own cells and look it up on the chart. And how do you know which one to make oxidation? Voltaic cells and galvanic cells are always spontaneous, which means they have to have a positive E value. So with the zinc one was the one that had to be flipped over to be made positive. So when we add them together, we get a positive E value. So that's how you are going to determine which one is the one that you flip over. Here's the way you're going to combine the half reactions, flipping, but this second rule is a little bit tricky. So write that down, and then we're going to try some examples. Here, we talked about this top part. We got to flip over one of the reactions to make it oxidation, and when you flip it, you're going to change the sign of it. And remember, you want to flip the one, that's the important part, flip the reaction, oh, I don't want it really in blue, but that's okay. Flip the reaction that will give a positive E when the reactions are added together. So that's how you know which one to flip. The other tricky part is when you balance it. Remember, like if one of them is 2E minus and one of them has 3E minus, you have to make it 6, so you multiply 1 by 3 and 1 by 2 and you add them. When you do that multiply by an integer, you do not change the E. So don't ever multiply the E's by numbers. It allows the reaction to occur for a longer period of time, but it doesn't give us a higher voltage. Okay, so keep that in mind. Now, here's the way your problems are going to look. So let's do a couple of these together. It says sketch a galvanic cell based on the reaction, and then we've got all this stuff that we're supposed to do. So let's sketch. And you know, I can't draw, so like if I can do this, you can do it. So if I got to sketch it, I'm going to make me some beakers. 2 beakers. I'm going to make me a U-tube. And of course it's got electrolyte in there. A little solution.
It's amazing.
Okay. Now, I have magnesium solid as one of my electrodes and aluminum solid. I can see that from the reaction. So one side, I'm going to put a strip of magnesium. And then floating around, I'm going to have magnesium ions. So make sure you include the ions in solution as well. And then on the other side, I'm going to have a strip of aluminum. And I'll put the aluminum ions inside.
Well, we have to draw this at some point.
Yeah, why not? Or at least label it. And there's my wire. So I need to label the anode and the cathode. The reaction is given, so I can already see that I have Al3 plus becoming Al, and I have Mg becoming Mg2 plus. So those are my half reactions on the side. Is Al being oxidized or reduced? Reduced. If it's reduced, is it the anode or the cathode?
Cathode.
Cathode. So I'm going to label the aluminum side as the cathode, which means the magnesium side is the anode. And which way do the electrons flow? Anode to cathode, alphabetical order. So I need to show the flow. Show the flow. Okay, so I've got the electron flow, I've got the labels. The only thing I don't have is the balanced reaction and the E. So you guys need to go back to the chart and find the half reactions. I'm going to go off this page for a second. Here's my aluminum reaction with a value of negative 1.66. And here's my magnesium reaction. But what do I have to do to that? I have to change the sign because this is the one that became oxidation. So I have here, I don't think I can write that spell, negative 1.66 volts, and I have positive 2.37 volts. And so for the total E, I just add them together. Even though we've got 2 electrons, 3 electrons, I'm never multiplying them by anything. What does that equal? 0.71? 0.71 volts. And then I need a final balanced reaction. So to do the final balanced reaction, I can multiply the top one by 2 and the bottom one by 3. And I'll get 2Al3 plus, 3Mg, 2Al, 3Mg2 plus. So there's all the pieces. Right. So last example, the equation is not given to you. So you are going to have to kind of figure out which one that you're going to flip over, and you're going to have to draw it and all that good stuff. Now, just to make things a little bit different, on the second page I had said something about a salt bridge or a porous disc. You can put a porous material between the 2 compartments as long as ions can flow through. They'll be able to equalize the charge. So I'm going to draw with a porous disc this time, just for fun. So I'm going to make a gigantic container and put a porous disc in the middle. There's my disc. See, that's a little bit easier. I don't have to draw 2 containers or a U-tube.
Is that like more efficient?
I don't know, it depends on what you like. Okay. So I'm going to have silver as an electrode, and I'm going to have hydrogen as an electrode. The nice thing about this is I can go back to my chart, and I can just find the silver, common silver electrode over here, this Ag plus. That's E minus yields Ag, and I kind of went offline there, should be the 0.8. And then the hydrogen one is right here. Now notice, these half reactions are already balanced. Just copy them down. Like, you don't have to balance that part. It's already done for you. So we go back, and I just copied down what I had seen. Ag plus E minus yields Ag, and the voltage for that was 0.80. And then the other one was 2H plus 2E minus yields H2. And the E for that was 0 because it's the standard. Okay? Which one am I going to have to flip over so when I add them I get a positive value? H, because if I flip the Ag I get negative 0.8 plus 0. That's not spontaneous. So I'm going to flip this guy over. And the voltage is still 0. And then the final E value is going to be 0.8 volts plus 0, 0.8 volts. Easy. Okay? Is the Ag the oxidation or the reduction? It's the reduction. The one we flipped is always the oxidation. And so now I'm going to put them in here. With silver it's pretty easy because I can do a strip of silver with silver ions floating around. But the hydrogen is difficult because can I have a strip of hydrogen?
No.
No, you can't have a strip of gas. So if you have something where both parts of the reaction are aqueous or they're gases or gases and aqueous, which is what we have don't have a solid to put in, what you do is you use a platinum wire. We use platinum because it's very unreactive. And we use the platinum wire as our wire. And then what we do is we kind of bubble in the gas around it. So this is supposed to be a tube with me bubbling in hydrogen gas. And then I'll still have the solution here, and this will have hydrogen ions floating around in it. So I bubble in the gas with a platinum wire. Okay? Now let's label, which one's the anode? Hydrogen, because oxidation always occurs at the anode, meaning the silver is the cathode. And so the electrons go which way? To the left. So make sure you show which way they go, because that's part of it. And then the last thing I really need to do is I need to balance my redox reaction by multiplying the silver through by 2. And that's it. I've done everything. I've got the voltage, I've got the labels, I've got the direction, I've got the anode, the cathode, all the stuff going on here.
We have to write states of matter.
You don't have to, but just keep in mind if you're not, like, recognize when you don't have a solid and you're going to have to use a platinum wire instead. You also have one in your homework where everything is aqueous, so you have to, like, just put a platinum wire and put all the ions floating around in the solution. So I have on this last slide just everything that should go into the cell. If you're drawing your own cell, doing the description, those are all the things you need in there. The potential, the balanced equation, the direction, the designation, and then like what's all in the different compartments.